in general, if we are looking at, say, y equals a to the x, where a is some number greater than 1, so we have a growth function, then that basic exponential is going to look something like that. So we've been talking about what can we tell about the graph of the derivative if we know the function. So, go ahead.
It's going to be undefined at y equals 0. Right?
Okay, that would be, yeah, so it's defined everywhere. Its domain is all real numbers, so it's defined everywhere. But what's happening is you go way out there to the left.
Closer to 0?
Yeah, the tangent lines are going to approach 0. So much like the original function, as we go way out to the left, our derivative graph is going to have to approach 0 as well. Does that make sense? Now, this thing, is it increasing or decreasing?
Increasing.
Always. So its derivative must be
Positive.
always positive, much like the original, because it's always positive. Anything else we can tell? So as you look at those derivatives, so we look at concavity. As you look at the derivatives, you have small positive, a little bit bigger positive, bigger positive, bigger positive. Since the slopes of the tangent lines are getting bigger, then the derivative is increasing, which means that the second derivative is going to be positive or negative, which means the derivative function is going to be increased. Well, let me back up there. So we look at the slopes of the tangent lines, they are increasing. And so this should have the derivative graph should be increasing as well, much like this. Kind of crazy. Well, it turns out that the derivative of a to the x, where a is any number bigger than 1, is going to be that same number a to the x times a constant. And the constant is a little bit annoying. It's the natural log of the base. So what that means is, if we say f of x is 5 to the x, then f prime of x is going to be
5 to the x times the natural log of 5.
Yeah, 5 to the x times the natural log of 5. Okay, well this isn't our favorite derivative yet. If we say g of x is 7 to the x, then g prime of x is going to be
7 to the x times the natural log of 7.
nice. Okay, you ready for it? Here's going to be our new favorite derivative. The derivative of e to the x.
I caught it.
You saw that coming?
Yeah.
So it's going to be e to the x times the natural log of e. But what's the natural log of e? 1. Can you believe it? The derivative of e to the x is itself e to the x. So what's the second derivative of e to the x?
E to the x.
And the third derivative. And you get the idea. Isn't that amazing? So that's pretty cool. So let's use our newfound knowledge, find the equation, or let me say find an equation of the tangent line to, we will say f of x equals e to the x x equals 1. So to find the tangent line, what do we need?
would just easily get.
Well, a tangent line. So we've got our curve.
Oh.
So we've got our curve y equals e to the x, and at the point 1, we're trying to find the equation of that tangent line. So it's an equation of a line. So to find an equation of a line, we need
A point.
point and a slope. So what's the point going to be?
E.
1 comma e, right? Because 1's the x coordinate. And you plug that in, you get e to the first, which is e. So there's your point. And now we need a slope. And how do you find slope?
It's just E.
So you take the derivative, right? Well, that wasn't very hard. It's e to the x. You evaluate that at the point. So f prime of 1 is e to the first as well. So it looks like an alphabet answer here. If our slope is this and our point is that, then our equation of a tangent line in point slope form is going to be
N minus E. E. X minus.
there you have it. Okay, and we talked about normal lines in here. That might be a new idea. So this comes up quite a bit. So a normal line is a line perpendicular to the tangent at the point of tangency. Did we talk about that?
A little bit.
A little bit. So we haven't done very much, but a normal line, we say a normal line is a line perpendicular to the tangent line at the point of tangency. So in our scheme here, I'm going to draw the tangent line as blue. And the normal line is going to contain that same point, but it'll be perpendicular to the tangent line. So it comes up in physics. I think, I don't know a lot of physics. So something like when you swing something around and I don't know what it is, centripetal force or something like that. Anyway, there's some kind of force that goes perpendicular to the tangent. And there's another one, I think if you let the thing go, like you swing, like your, what do they call those old time kind of slingshot things, like David slaying Goliath, So that thing comes out. So if you're swinging something around, then it's going, and you let it go, it's going to go in the direction of its tangent. But there's some other kind of force, like when those track guys do that big weight on the chain, and they kind of swing it around. So there's some kind of force that's going perpendicular to the tangent. I don't remember what it's called, but you can look it up. What is it?
Oh,
It's centrifugal, I don't know what's what, but there's one out there. Okay, so let's find the normal line. So find the normal line. So we use the same point. So you're still using 1e, but now the slope is going to be, for the normal line, is going to be
The negative reciprocal.
negative reciprocal. So it'll be negative 1 over e. It just gets weirder, right? So now you have 1 minus e equals negative 1 over e x minus 1. Okay? Well, let me give you a big derivative. So f of x is, see what all we know. You'll say 3 to the x plus x to the third minus the cube root of x plus, we'll say 4x to the 3/4 power minus 1 over x plus x to the e plus pi to the x. So I'm feeling it now. The more I do this, the better I get, more
I think
creativity.
you can stop.
Creativity. Oh, got one more for you.
Oh.
Plus pi to the pi. There we go. That's my grand finale. All right. Find f prime. Okay, so first one, derivative of 3 to the x.
3 to the x times natural log of 3.
Very nice, there's a new one. Derivative of x to the third, this was a confidence builder.
3x
3x
squared.
squared. And take those when you can get them. So this is going to be
Negative 1/3 x to the negative 2/3.
nice. And this one,
3x over 1/3 4.
okay with that? Good. What x to the e?
E times x to the e minus 1.
Very good, because that's x to a number, so it follows the power rule. So you bring the exponent in front times and then x to the subtract 1 from the exponent. About pi to the x.
Pi to the x times natural log of pi.
Very nice. How about pi to the pi?
0.
See, after you learn, the more you learn, the more you have to be careful when you see those. Nice. Now, believe it or not, we can use what little bit we know about the derivative of exponentials to do some things that don't really seem like they fit. So I'm going to say g of x. See if you can reason your way through this. Let's do pi to the 3x power. I'm going to do e to the x plus 4 power. Now we're going to learn what we're going to call the chain rule eventually with how do you take a derivative of the composition of two functions, which will be kind of surprising, but a big deal. We don't know that yet, so the workaround here is you're going to have to be clever with your properties of exponents to make this into something where you have a straightforward exponential. So we only know how to differentiate. Like if we had e to the x squared, we don't know how to differentiate that right now. We need more firepower. That's still to come. So because you don't just have e to the x, you have e to another function, this requires something known as the chain rule. But these, we don't know the chain rule. We could do these with the chain rule, but we don't know that. So we have to be clever with how we use our properties of exponents. So before we try to use our calculus, how can we make this be something to the x?
Pi to the 3 plus 5.
So remember when you have these properties of exponents, when you have x to the m raised to the n, you go x to the mn. So we're going to go right to left on this one. We have a 3x. So we can write that as,
X to the third to x.
yes, so pi to the third to the x. Can you see that? So if we think of it that way, then when we take its derivative, that's really a to the x, which we know is the derivative is going to be a to the x natural log a. So what will that look like?
Pi to the 3x natural log of 5/3 to the third.
That okay? And then if you wanted to flaunt your extensive knowledge of properties of logarithms, you could say that natural log of pi to the third is,
3 times.
so you could actually call that pi to the 3x times 3 natural log of pi. I don't know if that scores any better, but it's kind of impressive. Okay? Now how about the next one? We have to do a different property of exponents. Can you see it? Maybe, maybe not. So if we have x to the m times x to the n, the property of exponents we learned way back in our Algebra 2 days, maybe even Algebra 1, you said that's going to be x to the m plus n. So now we're going to go right to left again, because we have an addition in the exponents. So we can write that as e to the x times e to the fourth. Now you have a constant. Remember, this e to the fourth is just a constant times e to the x. So the derivative of a constant times a function is the constant times the derivative of the function. Follow all that? So the derivative of this is going to be that same constant times the derivative of e to the x, which is, now it's got an x in it. Remember, our derivative of If it was just constants, would be 0. But now it's a function because you got that x in there. So this is our new favorite derivative. It's going to be just, so you're going to get right back to e to the x times e to the fourth, because the constant times the derivative. Well, we can go right back to where we were. That's going to be e to the x plus 4. Crazy stuff, but kind of fun. So h of x is going to be e to the 5x plus, what other kind of crazy constant are there out there? 7 to the x plus 2 power. Okay, and we're going to find h prime. Being clever. We won't always have to be this clever, but it is kind of fun to be clever every now and again. Plus you get a chance to use those properties of logarithms. Those are good days. So what are we doing with that e to the 5x? We're going to think of that as e to the 5th to the x. So that's still h of x. So when we go to differentiate it, we're going to get
e to the 5x.
So yeah, e to the 5th to the x, so the same thing back, times.
Natural log of e to the 5th.
That's a log of e to the 5th. Oh, but we can't stop there because we know that a logarithm-based Euler's number and an exponential-based Euler's number are inverses of each other. So the natural log of e to the 5th is actually 5. See it? Crazy? I bet that's not a coincidence. Okay, how about the 7 to the x plus 2? 7 to the x times 7 to the second. So we have a constant times a function. So its derivative is going to be 7 to the x plus 2. So I'm going to do it, it's going to be well, almost. The constant times 7 to the x times the natural log of the base. And then again, you go back to the 7 to the x plus 2. You still have to have that natural log 7. Good, 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 good. All right. So, do a little practice for the test tomorrow. Any particular kind of problem you'd like to do? A hard one. Should we do some graph of derivative from the graph of the function? I can throw in some kind of crazy stuff. These are generally pretty tough, I think. So here's going to be our original function. I'm going to put a couple of tick marks down there so we actually have some scaling, and I'm going to do it on the x as well. This I don't really care so much about, at least so far. I think I'll stop there. So what we're seeing is this is supposed to be a cusp coming right down in here. So that's a cusp. Then we have, it looks like an absolute value, but there's a straight line segment, And then this is gonna be, this is supposed to indicate a vertical tangent right there. And then it's gonna kind of level off here, and then right at the end, it's gonna become just a horizontal line. So that's not an asymptote, but it's actually a horizontal line segment. I'm gonna say, and I would assume that this, where this straight line comes to this other curve, is gonna be a corner point. And I'm gonna assume that looks like a corner point as well. Corner point, so that will affect what your derivative looks like. You have 2 minutes. Right, should we do it together here a little bit?
Yes.
Okay, no, you go ahead and try. So,
Yes, let's do it together.
okay, so this I would say, this is a judgment call. Is that 0? Is it a little bit negative? That's your judgment call. Right, that won't be right or wrong there, but it's definitely not positive. So it's going to start, I'm going to say it's a little bit negative. It starts below the x-axis. It's going to go steeper, 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 fall off the cliff negative. A cusp is going to lead to a vertical asymptote in the derivative. We hop over the asymptote, and now it's a really steep positive. So it's going to come from up here. So cusp gives us a vertical asymptote where they go in different directions. Now this is going to end up being, I think, some positive number right in there. Corner point means it's going to be undefined there. Now the straight line segment, the derivative of a straight line, is its slope. So the slope looks like it's down 2 over 1 is a negative 2. So it's going to be, again, undefined at the corner point, undefined at the other corner point, but a horizontal line at negative 2, which is its slope. Okay? Then they're going to get a positive 2, so it's going to jump up to positive 2 and go to a corner point. Now that looks pretty close to 0, and then it's going to go steeper, 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 fall off the cliff, negative infinity. So it's going to go something like that. Up over the asymptote, still negative infinity, so now it's coming from down below here. And it looks like it's going to get a little bit negative there. So it's going to end where a corner point where it's undefined. And now the horizontal line is going to be just slope 0 all the way through. You might need a little more practice on those.
Yeah. Way to hand me the eraser.
Mine was just reading.
Yes.
Oh, you do? Wendy's.
Wendy's fries and exhibit street.
And a calc book code.
I wonder if this is.
Oh. See, you get some help on these, Evan?
I was just mostly getting them right on the quiz. I just forgot about the
You said something.
so I was like getting to the right point, I think.
Okay, make sure you try the review.
Yeah.
If you get stuck, call
Yeah.
somebody.
Thank you.
Yeah.
Oh, no. I get it. $400 Street, we should just review for the test today. Just abandon the legend.
You know, I'm down with that. I can get jiggy with that idea.
You know, because every time that I feel like I'm good, you know, you can't ever be too prepared.
What's with my pencil? Not only is it 420, we have it Magoo McGoo and Shirley Cohen. Has to be a little bit good.
Don't lose swine flu. E-T-U-N-G-O. And swine flu.
passed down.
I mean, if we're doing it, there's gotta be other people who will do it.
It's book 420, and the names are Magoo, McFoo, Sherman, Kung Fu.
No, Shermu.
Oh, Shermu Kung Fu, and then
No,
Tungmu
Tungmu's
Swine
Fun
Flu.
Flu.
Now it's up to next year's class to,
It is up to next year's class.
who's in Calc now that's gonna be in Calc 2? Cause everyone that I know is a senior now.
The same.
There's gotta be some juniors in there.
Yeah, there's some in my grade, so I don't know. I don't know anybody in my
Is it?
front about this.
That's what gets book 420.
I mean, there's so little calc books that. Tungmu's Fun Flu. Oh, man. I should probably leave this out so you can disinfect it or whatever.
I don't think he disinfected the other ones. Dude, I'm gonna really self-sort them out for the game. Cause I wasn't gonna let Caduce outdo me on deadlift.
What'd you do on dinner today? What'd you do?
I just did, I didn't go like heavy. I just did 2 reds and a green.
So 60, so you did 299.
But Caduce was doing 2 reds. He was like, you're looking little today. I was like, don't ever say that.
Don't you ever say that to me,
Put
boy.
the green on, cranked out 5, and I was like, you do it now. He couldn't get it out, and I was like, yeah, that's right.
So I'm gonna do a little bit of housekeeping here, so while I do that, is there one particular kind of problem we can do for practice, or just?
Oh, I was, hold on.
What?
Put me on the spot.
Yeah.
Okay, I have the projections pretty much down. Let's just do, Alex, is there anything you wanna do? Oh, can we do a fraction D, fraction D comp?
pull one from the text. That'd be good.
Yeah.
Yeah, give us like.
Oh, and that might make it quicker to grade tomorrow.
Exactly, I mean,
Why didn't I think of that?
best of both worlds.
And then,
Yeah, it's
like,
a
you do one
win-win.
of the ones that's like the AX plus B.
Yeah, let me give you one of those. So I'll give you, this is gonna be a messy one. We'll do a repeated quadratic. Irreducible quadratic, so.
Believe it or not, I went home for one.
X squared plus 5
I constantly said one of my friends.
squared plus 1.
We were,
Oh.
we were in depth in talking about it last week. Out of this car. It was just like, I was surprised, you know. I was not sure.
Okay, everyone assume your position.
You literally smelling my hair. Step away from my, step away.
I'm smelling my own breath, that's what the mask does.
Oh, please not in the bedroom.
So,